All right, in this lecture, we're going to talk about direct computer methods for solving linear systems of equations. So recall from our review of linear algebra that there are basically three rules that we can perform on systems of linear equations that will not change the solution. So three manipulations. One of those is to switch two rows and columns. Two rows or two columns. That will not change the solution. Any row can be multiplied by a constant without changing the solution. And any row or linear multiple of a row, so that's sort of a linear multiple means applying the operation to, can be added or subtracted to or from a row without changing the solution. So we'll see an example of this in the next slide or the next couple of slides if you're not familiar or you don't recall these rules. So let's start with a very simple system of linear equations. And what we're going to do is we're going to write those just to make the manipulations a little bit more straightforward and head us towards a computer implementation of this. We're going to write those equations in this so-called augmented matrix form. So you can see on the left side of this dashed line is simply the coefficients of the x1 and x2 in the two equations, and on the right hand side are the constants, the right hand side of the equations. So if we proceed with these matrix row operations, and I've written above these lines, the r's correspond to the rows. So this is basically we're multiplying the first row times the constant minus 4/3 and replacing the first row with that. And so that manipulation results in the second term. And then if we add the first and second rows and replace the output of that with the second row, we get this third term. Now, once the matrix is in this form, that is where all entries below the diagonal are 0. We call this row echelon form. So again, this is a simple two equation, but it would be the same if you had say a 3 by 3 matrix. You'd have some entries on the diagonal, and then you'd have zeros below. That would be what row echelon form would look like for a 3 by 3 augmented matrix system of equations. So this is called row echelon form once we get to that point. Now, just to make things a little bit more clear, what we're going to do is just go ahead and make the diagonals 1 by using our rule 2, and that is multiplying a constant. In this case, we'll do them both in one step. So we'll multiply the first row times a quarter so that we have a 1 on the diagonal, and we'll multiply the second row times 3/14 so that we have a 1 on the diagonal, negative 3/14 so that we have a 1 on the diagonal. And now that we have the matrix in this form, let's just write down what these would be in equations, right? So the second one would be simply x2 is equal to 17/7. And the first equation would be x1 plus 8/3. x2 is equal to 10/3. So now all we have to do, since the second equation already represents the solution for x2, we can simply plug that back into this equation and solve. And if we were to do that, we would ultimately get x1 equals minus 22/7. So this is the solution x1, this is the solution x2, and that is the solution to our system of equations. So this process of putting the augmented matrix in row echelon form, solving for the last equation, basically by inspection, and then substituting in from the last equation to the row above, and so on. This was called back substitution. And this entire process of putting a matrix in row echelon form and then back substitution is called Gaussian elimination. So let's look at a couple of properties of Gaussian elimination. One is the stability of the process. And in order to start our discussion about stability, we're going to go ahead and define a few more terms. If we have a matrix, in this case, our matrix A is just 1, 1, 1, 1.001. Any matrix or system of equations that would have this coefficient matrix, what we can do is we can check the determinant of the matrix. And if the determinant of A were to be identically equal to 0, then we would call this a singular matrix. A singular matrix does not have a solution, so there's no amount of Gaussian elimination processes or anything we could do to come up with a valid solution. It means there either is no solution to that system of equations, or possibly there are an infinite number of solutions to the system of equations. So if we go ahead and compute the determinant of our A matrix here, we can see that it's not 0, but it's very near 0. And in fact, if we were to change this term to be identically 1, then it would be 0. So since it's almost singular or near singular, we would call this matrix A ill-conditioned. And we also have a matrix B that we can see from the determinant. It's almost 1. It is not ill-conditioned. And the terminology for that is that we'll say well-conditioned. There is a notion of something called a condition number, which is basically a matrix's immutability to numerical computation. And we're going to save that discussion for later when we discuss the singular value decomposition. But so here we have two matrices. One, matrix A, is ill-conditioned and matrix B is well-conditioned. Now let's look at the conditioning of the matrix on the possibility of the solution of a system of equations. So let's illustrate that, the ill-conditioning of A, by looking at two so-called right-hand side vectors. So these are the constants on the right-hand side of the equal sign. So if we were to look at these two systems, again, the coefficient matrix is what we had before. It's A, right? But here we're going to look at two right-hand side vectors that are only a very, very small difference, right? So the first one is 2 and 2, and the second one is 2 and 2.001. Well, the first matrix has this solution, and the second matrix has this solution. And so what we see is that a change, a perturbation in the fourth decimal place of the right-hand side vector creates a change in the solution in the first decimal place, right, in the leading order. Even the most robust of numerical algorithms is going to have trouble with this kind of matrix conditioning. Okay, now let's look at another case where we consider our so-called well-conditioned matrix B, but let's see what happens if we don't design a good algorithm and we proceed with Gaussian elimination. So this time, we have our so-called well-conditioned matrix B with a right-hand side vector, column vector 1, 2, and we'll proceed with Gaussian elimination. So 10,000 times the first row plus the second added to the second row, or replacing the second row, gives us this. And then we end up with a row echelon form of that. And if we back substitute, we have this solution. So x1 equal to 1, x2 equal to 0.999. Now let's look at the exact same procedure, but on a computer with a machine epsilon of 0.001. So recall that machine epsilon is the smallest number that when added to 1 will produce a different answer. And so in this case, you could think of machine epsilon to be that it will round off, this computer would round off to 3 decimal places. If we proceed with Gaussian elimination, I'm only showing the final result here in row echelon form. I've omitted the sequence of steps, but this would be the reduced row echelon form we would get with this solution, right? 0, 1. Okay, of course that's not close to the solution we have above, which is the exact solution. However, let's see what happens whenever we just simply exchange the rows, the first and second row, before we start our Gaussian elimination. So again, looking at our first matrix, it's simply the original augmented matrix with the first 2 rows swapped. And again, we know that swapping rows does not change the solution. However, in this case, it affects the stability of the algorithm. If we proceed with Gaussian elimination, putting the final matrix in row echelon form and back substituting, we have here that the final answer is 1, 1. And we see that that's only different from the exact answer. All right, remember the exact answer was 1, 0.9999. So it's only different by machine epsilon, right? So if we add machine epsilon to the exact answer, we would get the approximate answer on our computer that rounds off to 3 decimal places. So you can see that even though we started with a well-conditioned matrix B, if we don't exchange the rows, then what happens is we have a poorly designed or not robust algorithm that can affect the solution vastly. Okay, so it's this row exchange that we're going to do is what we call partial pivoting. Remember, the pivot, if we pivot on rows only, we call it partial pivoting, and if we pivot on rows and columns, then we would call that full pivoting. But full pivoting would give you the most stable solution, of course, at the cost of some computational expense of having to track the permutations of the columns and do the pivoting. And so in most cases, only row pivoting or partial pivoting is done, row exchanging. And so that process we'll call Gaussian elimination with partial pivoting. And this is what pseudocode would look like for that algorithm. So pseudocode is just simply kind of human readable steps in a computation that could be implemented in a computer program. There's no syntax here for any specific language. So basically what we're going to do is for a system of equations that we'll label E1, E2 to En. And in this case, we have exactly n equations and n unknowns. We'll start a loop over the rows where I will keep track of the row number we're on. Okay, so as we're progressing through, the first thing we'll do is try to find the pivot by looking down the column from the ith row and finding the index P, which is the largest number below the row I, or from the row I down. If it happens to be that P equals to I, then there's no reason to exchange rows in that case, and we'll skip the step. But otherwise, we will exchange rows I and P, and then we'll start a new loop. Okay, so J will begin from the ith row down. Essentially, this is looking down the columns. We define a factor that eliminates all entries below the below the ith column, and we perform this operation. So the EJ, that's the jth row of, essentially it corresponds to equation J, is equal to EJ minus that factor times EI. So we're going to use the jth row to eliminate all of the I rows below. So after this, the matrix will be in row echelon form. And then we can start the back substitution, right? So that's just simply, once we have it in row echelon form, We can solve for xn, that's the solution at the last row, and then we just back substitute in, by going up the rows in reverse. So from the last row up, we just back substitute in all the answers. And this process, again, is called Gaussian elimination with back substitution. So there's another process that we'll call Gauss-Jordan elimination that starts with our matrix in row echelon form, like we have here. So this is our B matrix from before, after doing the Gaussian elimination, putting it in row echelon form. And then after that, what we'll do is eliminate above the pivots. So starting with the last row here, the leading non-zero entry, the pivot is 1. We'll eliminate all the entries above it. And once we've done that for every row, we'll simply normalize the diagonal entries to be 1s. And in that case, we can just read off the solution, right? So remember, if we were to write this back in the system of equations, this is just going to be x2 equals to 0.9999 and x1 equals to 1. So we can simply read off the equations. Whenever you have an augmented matrix that is in this form, where you have only 1s on the diagonal, and all entries below and above the diagonal are in zeros, this is going to be called reduced row echelon form. So again, this is on 2 by 2, so it might be hard to see, but if we had a 3 by 3 matrix or anything larger, we would have this, and then the augmented entries that contain the solution. All right, so that's reduced row echelon form. And our pseudocode for that is going to be similar. We'll loop over the rows. We're going to do pivoting the same way. So we'll look down from the ith row, looking for the largest entry. And if it's not equal to I, we'll go ahead and do the exchange. Once we've done the exchange, we will have an inner loop that eliminates now both below and above the pivot, creating zeros there. These are operations 5 and 6 that do that. And then once we have that done, there's no reason to back substitute because all we have to do is read off the last augmented entries. Just a note, because we do have this extra steps of eliminating below and above the diagonal, I want to say that plain Gauss elimination, so what I'll say, Gauss elimination with back substitution, is usually about 6 times faster than Gauss-Jordan. Again, because we have this additional steps of eliminating above the pivot as well. So typically we use Gaussian elimination with back substitution. However, the Gauss-Jordan process does have one nice feature in that for matrix inverses, which we'll talk about next, it has the same speed. They have an equivalent efficiency of Gaussian elimination, and therefore it's kind of a clearer way to look at how to do matrix inverse in this case. And so we'll only use Gauss-Jordan for matrix inverse operations, which we'll talk about in the next slide. So for a matrix inverse, if we have a matrix like this, and we want to compute its inverse, instead of augmenting it with a right-hand side vector, we augment it with the identity matrix. So remember, we're calling this the augmented matrix, where we have our original matrix A, and then here we have an identity matrix that is the same size as A. Then we just proceed with Gauss-Jordan elimination. In this case, we don't do anything different than we did before, so I'm omitting all the steps. And what we'll end up with is a matrix in reduced row echelon form, where now this is the identity matrix, and this is the inverse of A. So we can use Gauss-Jordan with no changes from the way we use it to solve systems of equations to also find matrix inverses.